Thank you for coming. Thank you for your interest. I'm going to talk about this project, multi-objective optimization of an industrial process of biomass conversion into energy vectors. And I'm going to show you a case study of sugarcane, transformation of sugarcane into ethanol and electricity. First, I want to spend a few words talking about the problem. The problem can be summarized in this simple question: how can renewable energies displace fossil energies? This is important because of, well, several aspects. I want to emphasize one of them. First of all, we have a lot of accumulated experience regarding using fossil sources. For instance, coal. We burn coal, we generate heat. With this amount of heat, we generate steam, and we have steam engines. In the beginning of the Industrial Revolution, that's what, let's say, drove the Industrial Revolution, and we have 200 years of accumulated experience. Regarding fuels for transportation, basically we have fuels from petroleum. We can do it from coal. The Germans during the Second World War produced gasoline from coal. Regarding petroleum fuels, we have, let's say, 100 years of accumulated experience. So renewable energies have to get into this scenario. First of all, we can say that renewable energies compete with fossil energies. In addition to competing, biofuels also have to comply with engine specifications developed for petroleum fuels applications. I mean, when we were developing the engine and the fuel that goes with this engine, both were developed together. Biofuel have to comply with this. You cannot develop a new type of engine which would be very efficient with this biofuel, bioethanol, for instance. So that's another problem regarding the introduction of bioenergies and in particular biofuels into this scenario. And of course, when we're talking about bioenergy, biorefining is a key technology. Just to state things, by biorefining I mean the transformation of biomass into biochemical compounds, just as in a petroleum refinery, but also the transformation of this biomass into energy vectors, for instance, electricity or biofuel, and also supercritical CO2. That's an idea that I'm just stating this idea. This may become very important in the near future because of carbon capture and storage. Okay, so let's move on. The basic objective of this work is to investigate and to quantify the impact of integrating new biomass deconstruction technologies into an existing agro-industrial production system in terms of its robustness and new multi-objective optimal operating conditions. So we want to investigate the impacts and how this new integrated system can be optimized and can be operated in a very robust way. I'm going to define these ideas very precisely during the presentation. To start this work, we start by defining what we call a reference agro-industrial system. This system is composed of three, let's say, you have your industrial unit, and you have all the field operations, harvesting and transportation of the biomass to the central unit, central industrial unit. So it's a production, logistics, processing problem. And to summarize all these numbers, I mean, to define the scales within which we have to work, consider that you have those 30,000 hectares multiplied by the average productivity, which is 70, and 5 megawatts of electricity, CO2, you have a vinasse, which is a kind of stillage, and also you have solid to make our study, to base our study, okay? So the problem now is to integrate second generation conversion pathways into these already existing first generation conversion technologies. How can we do that? There are several ways. a very promising integrating strategy can be summarized in this picture. You see that the idea is to harvest everything together. I mean, if you're talking about corn, you harvest corn and also the leaves. You bring all that to your unit, and you perform several mechanical operations aimed to separate, to prepare, and to eventually extract compounds or molecules that you can process through a first generation conversion pathway, second generation conversion pathway. Use a thermochemical conversion pathway. I mean, you can burn things to generate heat. Generation pathway can produce fuel, you can produce chemicals. The second generation pathway also gives you fuel and chemicals. And the objective of these processes that are here, ferment, we're calling residues, you burn them, heat and electricity. So that's an idea of how this could be done, integrating first and second generation together. And you also have 1 degree of freedom here, which corresponds to deciding the amount of notable and the amount that are to be burned. Okay? So just to detail a little bit more, this is what happens in a first generation typical sugar mill. You have sugar cane being delivered at the plant, the industrial facility. You have mechanical processing. You separate this to extract those molecules that you can send to the first generation conversion pathway. I mean sucrose in the case of sugarcane. And what you cannot, we call bagasse. Bagasse we're going to burn, or is the humidity rate of bagasse, which has to be around 50%. So you produce steam, CO2 here, and water. Of bagasse and straw, fermentable, it's going to be burned in conversion pathway. You have to it's dismantled, then you have a very fine, you have to depolymerize these large molecules made of glucose monomers, for instance. And those sugar, you can do more, a little bit more, I mean. You can send some of these fermentable sugars or some of its byproducts to what we call a biorefinery, and you can produce biochemicals in this enhanced second generation industrial process. Okay, and that's what I was talking about. You can, I'm going back one slide. You see that with this strategy we are producing ethanol, electricity, and chemicals. I forgot to draw the arrow here, chemicals. So you draw the money symbol. So that's a point, an important point. But I want to draw your attention that we're emitting a lot of CO2 here. This CO2 generates revenue, I mean carbon credits. So if you employ another type of technology, instead of using air, but I think in the near future this is going to be a very important idea, because you know fossil fuels are coming back very strong, especially because of these new sources being not that they were not known before, but they are now viable due to new technologies. I'm talking about shale oil and gas. Okay, so let's move on because I don't have all that time. So now I'm talking about modeling. We have this reference sugarcane unit. We already defined the scales that we have to work around. And so now I have to describe how we're going to model this process. So by model, I mean a system, which is represented here. This system has inputs, two types of inputs. Let's say the red arrows and the green arrows. I'm going to explain that. This system has inputs and outputs. Outputs are products of interest, which generate revenue. The inputs, we can think of two types of inputs, what we're calling process variables and control variables. Process variables can be fiber content of biomass, humidity, ambient temperature, for instance. I mean, these process variables are, in principle, those variables that I cannot control. On the other hand, what we're calling control variables are exactly those variables that I can or that I want to control. For instance, the combustion temperature in the boiler. I can control that. What we call inputs, two types of inputs and outputs. And using Gibbs vector notation, is the vector of C is projecting sin C into, so just we reason distribution of the fiber content. Okay, so F, the system of transforming variables into probability density functions. The function F is the probability density function of the output variable. It's our input vector, here, 15 input variables, and so on. Our control variables are, actually, we're in this first study, we're considering that all straw, 100% of straw is burned, okay? So we are going to vary, we're going to control the amount of burning bagasse and the amount of hydrolyzed bagasse. And we have a second one, which is the input biomass, represents the average sugarcane mill. So that's our system. This is what we're doing. We're working in terms of probability density functions, these variables that are shown. And let's see the results. First of all, let's see how things are being varied. First generation ethanol comes from juice, which is converted 100% through first generation pathway. The amount of electricity generated from burning straw is also fixed because we're not deciding if we want to hydrolyze it or not. So these two variables, or these two parameters, are actually baselines of our production outputs. I'm going to show you this in a few seconds in a graph. Okay, the other ones are being varied. Rate of burning bagasse, fiber content, water content, and so on. You have in this table, you have the lower and upper limits. You also have the nature of these variables. You see, let's look, for instance, fiber content. Okay, fiber content varies between 35% and 40%, and it's considered to be uniform random. Why random? Because we cannot control, okay, but why uniform? We are considering a uniform variation of the fiber content because I cannot control. So a uniform variation is the worst thing that can happen regarding the conversion process, because I cannot control the fiber content and it varies randomly, uniformly between 35 and 40%. So this is a kind of a worst case scenario. Okay? Yeah, that's it. Let's move on. Just to show you, I need to explain how the results can be plotted into what we call an operating envelope. An operating envelope is a graph in which you have all your output variables defined as what I call ethanol production baseline. So that's the minimum amount of ethanol that I'm producing. And this is associated with fermentation of sucrose, okay, which is not varying. Also, you have a minimum electricity production, or the baseline power generation, associated to burning straw, the decision of burning 100% of straw. Okay? Now, you have another curve here, which is what we call Pareto frontier, but actually it is an energy conservation limit, because those two variables, electricity and ethanol, are energy variables. And they cannot exceed the amount of energy that is entering the system. So you have a limit to the right of these baselines. Okay? So somewhere you're going to have an energy limit which is associated with the Pareto frontier. Okay? Pareto was an economist, but his ideas are very bright in terms of how to interpret these results. Okay? So another point is that singles of these curves, the baselines in the Pareto frontier. Okay? So a single set of inputs will produce you a single set of outputs which can be represented as a point in this graph. Also, another important, so that's the operating envelope. And another important feature to understand the results is what we call the target operating region. Okay? Because the Pareto frontier actually represents the maximum amount of output variables that you can get. The Pareto frontier is constituted of points that we call non-dominant points. I mean, you cannot increase power generation without decreasing ethanol production. Okay? And that happens only on the Pareto frontier. Okay? So those are what we call non-dominant points. And of course, from the process point of view, if we manage to operate near the Pareto frontier, this is very nice because this is the optimum operation state regarding this two objective optimization problem. Okay? So let's move on. Those are the results that we got. Yeah. So what we did, we wrote all those equations. We varied all those input variables. We made 20,000 numerical experiments here. So each point is a set of input variables, and we can use formulas for this. First of all, let's identify the things that I was talking about. This is identified with respect to belonging or not to the target operating region. Okay, despite of the random variations of fiber content, bagasse, humidity, and so on. So if you manage to set your control variables in order that you get PDFs which are indifferent, so you have a very robust process. Because what's happening? No matter the fiber content, the probability of being near the Pareto frontier is the same. So let's see the results. To see that, to analyze that, we look at the output PDFs, so ethanol and electricity, and operation. You see, so this process or this pathway, conversion pathway, this pathway, which corresponds to burning hemicelluloses, is an optimization problem. The optimization problem is to set the control variables in order to obtain increased probabilities of getting operating states within the target operating region, where you have maximum conversion efficiencies, because we're near the Pareto frontier. We are near the energy limit line. Okay? And you obtain these maximum efficiencies despite the random variations of all intervening variables, fiber content, humidity, and so on. So let's look one result, first of all, which we consider validation results because those results are actually known a priori. Okay? We know that this is fiber content. You're going to have a very efficient process in a probabilistic view. Okay? And the same applies to fiber content. The more are the probabilities of having an optimal conversion process. But we call that validation results because qualitatively they are behaving. The results are as we expected, but also quantitatively we know that 50% of water content is a very known number in the field because we have this 30 years of experience, let's say, the constituents of fiber, hemicellulose content or cellulose content, hemicellulose content, and lignin content. So you have the PDFs, so the operating envelope and the target operating region. Okay, the black curves are the PDFs, so the operating envelope, and the red curves are the target operating region. So if you look at the PDFs, the red PDFs, what do you want? You want to have a high probability of being optimal. Okay, so you want very high value points in the red. It's surrounded by types of molecules. Okay, so this explains why it is more interesting to have lower contents of cellulose. Okay, and on the other hand, the same applies to lignin content because of two basic factors. Lignin has a very high heating power. It's almost the double of cellulose and hemicellulose, and it's not a polymer actually. It's meant for energy conversion. It's interesting to have a lot more lignin. This is the kind of information that this type of model gives you. Okay, so in conclusion, I'm concluding now. These results reveal very useful information for optimal and robust plant operation. I mean, the decisions that the operator have to make in order to be optimal, in order to increase the chances of being optimal, but also these informations are important for long-term planning regarding plant breeding, for instance, plant breeding for biomass, and also regarding development of new equipment and processes, which authorizes us to conclude that there will be a new development cycle regarding all these technologies. Okay, so that's it. Thank you very much.